This video is how to check an isolator using an inexpensive spectrum analyzer with a tracking generator. I've put a bullet in here to connect the tracking generator through the cable to the input spectrum analyzer and normalize it to, this is 0.01 now, so that's close enough all the way across there. And if I remove the bullet here, we'll see the isolation. So the isolation between these cables, and I'll move it around so you see it doesn't come up, is about 61 dB. So good enough for this test. Now we're going to take this Telewave unit that is an isolator. The idea is signals going to the input here from the transmitter and go out the output here to the antenna or to some other, maybe a cavity, whatever it's going to. And any reflected power would come in here. Instead of going back to here, it would go down through to here. And any power that actually came through to this one would go to the load here, so that none of the power gets back to the input here and into the amplifier, which could cause heating problems, it could cause VisWire problems, etc., etc. So if the antenna fails or the antenna has a high standing wave, that will not impact the amplifier because the amplifier is isolated by this isolator. I've connected the transmitter to this, the transmitter being the tracking generator. The output here is the equivalent of the antenna, so the power going out to the antenna, going into the spectrum analyzer in this case though. And we got a total bandwidth of 150 to 156.5 at the half dB points, or well, it's drifted a little since I started it here. It says 0.43 in the 151.5, which is where it's supposedly tuned. It looks like it might be a little bit off, or this might be a little bit off, hard to say. But anyway, so we got about 6 megahertz, 6.5 megahertz of area where you don't have very much loss. Now I've turned this thing around, that's why I reoriented it. I used the B and C's here because it makes it simpler to do this. If you want to do the absolutely best test, you want to go directly on with the appropriate connectors. But anyway, for this just quick evaluation, I did this, and we have the same scale here of 5 dB per division, so it's going way the heck down. According to this, it's minus 60, 61, so that's the noise floor. So it's at least that far down at the 151 frequency. It's 27 and 28 here at the other two frequencies. So as you see, it does degrade as you get further off frequency. So let's change the scale here because this is just reflecting what it's measured. This will change the scale to 10 again. Now you see where we're at. Now, according to this analyzer, this thing's not tuned perfectly on frequency. However, you will see differences between instruments, and between this and what this was tuned up on, I'd probably trust the professional machine that was used at Telewave that tuned this more than I would this thing. But the point is that you're down 61 dB, and actually this is down even around 70 dB. But we're down in the area because of the fact the noise level is also in that same region where it's hard to say. This may actually go down here and then come back up. So it may even be 75 or 80 dB. That's one failing of this particular unit, is there's a lot of leakage between this port and this port internal to this instrument, which is a reason to buy a better instrument if you have the wherewithal to do so. But anyway, you see that in the reverse direction we have at least 60, probably more like 70 to 80 dB of isolation in the Telewave unit here. So obviously this is doing its job and it's tuned in the center here. But we have this unclarity due to the leakage that's in this particular unit at that kind of power levels. Okay, I've pulled the cable off here and recorded the line here of what the noise level is and leakage level of this instrument, so that we can see that this anomaly that we've been talking about is actual, and it's caused by this leakage. You notice the trend here is to go down. The trend on this side is also to go down. And the likelihood is that they cross down here exactly where tuned, which is probably 75 to 80 dB, or whatever the spec is probably what they tuned to. So once again, I say this line represents the lower limit of what you can test with this particular instrument and consider the results to be reliable. I think it's good down to the line, but it's probably not so good once you get down below that line. Let's look at the worst case scenario. I've got power coming in here, should be going out here, but I've got no load whatsoever. So I have total return of the signal, it's infinite viswar. This is still on, and this is on. And I'm looking at the power that's coming into the load that would normally be here. And it's exactly the same as the amount of power that's coming in from the input here. So the input's going right straight into this load because it's being reflected back from here. Nothing's going out there, nothing to go to. So you see that it's almost exactly the same trace as what we got on the output port when there was a load here and the output was matched. And that's what it's supposed to do. So typically the power from a mismatch coming in this direction would go into here first and then into here second. So there would be some loss going into this load. So if you're going to put in two different loads, you want the big one here and the little one here. At Telewave, we use the same size. This is the same size as that one. This is up to, I think, 70 watts on this particular one. Let's take a look at that as a matter of fact. So I've swapped these two. I have the load here. I still have an open over here. Power's coming in here. And the amount coming here looks like about 20 dB down, 22 dB down. Let's say it was 20. 20 is, it would be 100 milliwatts out of a, no, let's say it'd be 1 watt out of 100 watts. So 22, let's call it 23, would be about a half a watt that would be going into the dummy load that normally would be here. But most of the power would be going into this one over here because that's where the discontinuity is on this side. So I've restricted myself to using an instrument here. It costs about $1,500 and represents the low end of what might be useful for this checking out of isolators. But we'll have another video that goes into more detail and gives you an idea how a two-port device like a network analyzer will give you a lot easier time of it, especially if you have to tune things. And we'll give you a little better results on exactly what the levels are of isolation that you can get with this device. In summary, first, normalize the spectrum analyzer and tracking generator. Second, confirm that the noise and leakage is better than 60 dB down. Third, connect the tracking generator to the input and the spectrum analyzer to the output of the isolator. Fourth, reverse input and output to check the reverse isolation. Fifth, look at the worst case scenario, output open or shorted, which is infinite viswar. Sixth, measure the power at the load furthest from the high viswar output, which will be less than at the close load.